Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
So the derivative as a function, what is it, why is it, why are we using it, where can it be, things like that. If you haven't heard of it, there is a video on YouTube called I Will Derive. And I think that the video, well, I mean, it's cute and humorous, but I like some of the visuals that are in that. And if you watch it before you learn a lot about derivatives and then you watch it later after you really gain a great foundation on derivatives, you will understand a lot more of what's going on in it. But I do like some of the graphics they have. So as stated in my previous video, we know that given a function f of x, we can find its derivative by doing the limit as h approaches 0 of f of x plus h minus f of x all divided by h. However, there's some caveats to that, okay? To derive something, it must be smooth and continuous. Now, I have an entire video on continuous and continuity and what it means, okay? You can't pick up your pencil. So here, an absolute value graph is not smooth. Now, we could cut it into two linear parts and derive each of them separately, but we cannot derive the function as a whole, okay? Again, this gap here would be not continuous. Now, even if it comes up and it comes to a little cusp, that's that sharp point. That sharp point means we're not smooth, okay? So these three examples you could not derive. So to be able to derive a function, it must be smooth and continuous. Now here's the small catch. On an interval a, b. Because graphs have different behaviors at different places, remember? The derivative, we can find it to get the instantaneous velocity. So if we're just looking at one window, I don't care if it has a gap or a jump in it, like way off in the distance. If I'm just looking over here, well, I can do the derivative of this part. That's going to have a completely separate behavior than when I pop over here. Okay? So let's look at some quick notation as well. All these will mean derivative with a little dash by the f, a little dash by the y. dy, derivative of y with respect to x, derivative of the function with respect to x, the derivative with respect to x of the function, the derivative of the function, the derivative with the x of the function. That is 1, 2, 3, 4, 5, 6, 7 ways right there that they could denote this, depending on how they chose to write. So just keep in mind that they all mean the same thing. We're all deriving. Okay. So I've just drawn an equation, and I want us to think about the slope of the tangent line. And if you watch that I Will Derive video, I don't even remember who did it. You'll kind of see this. I'm going to use this little fobby thing. So a tangent line can only touch in one point. So here, the tangent line would be uphill, right? Positive slope. And as it slides along, and it slides along, and it slides along, you see, and this is part of what I like about that thing, right here, what happened? The slope of the tangent line is 0. Well, think about this. Let's say this is a graph of a basketball's height over time. So at this time, let's say the arrow is on the ground and the basketball is going up, 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 up. After a couple seconds, the basketball starts going down, 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 down. What kind of speed does the basketball have to hit in between going up and then coming back down? It has to hit a velocity of 0. And that happened at the peak, right? So when you're at a peak, your velocity has to hit 0 because now you have to come down, right? So now the ball is coming down, 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 down. And then it hits something. And we have a tangent line of 0 again. Maybe it landed on a table, who knows? And now the ball is going back up, 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 up. So that here, it was uphill, so the velocity or the tangent line was positive. Then the slope was 0, right, or the velocity. Then we were going downhill, so it was negative velocity. Now we're going uphill, so that's positive velocity. So all these things are going to start relating to each other, okay? But this is really, really big, knowing when the velocity is 0, because knowing when the velocity is 0 means that you know where the peaks and the valleys of the graphs are. So probably up until this point in your mathematical career, you've just been using your graphing calculator to find maximum and minimums. Once we really grasped everything about our tangent velocities, we are really going to be able to find all those pieces of the graph without the graphing calculator. Okay, now, not only can you do one derivative, you can do higher order derivatives. Okay, so you can do the derivative of a derivative. Okay, so another way they might write that is d2y dx squared. For some reason they don't put the parentheses around it. Or you'll see it as the second derivative. Or you'll see it as the second derivative. You can do multiple derivatives. This can continue on, okay? So the third derivative would be 1, 2, 3, or it'd be d3y dx cubed, etc. Okay? So when you're working in physics, if you start with a position, and this is your f of x, then your first derivative gives you your velocity, or your instantaneous, actually I should say, rate of change. How fast were you going when you got that speeding ticket, right? And the second derivative gives you your acceleration. Okay. Now, here's some things that I want you to think about. Can you be accelerating and have positive velocity? Yes. Can you be decelerating and have positive velocity? Also, yes. So let's think about that. Let's say you're driving down the road and the stoplight ahead turns red. Well, you're going to start slowing down, but you're still going forward. So your velocity is still in a positive direction. Okay? So here, we're going up, 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 but we've got to slow down. Even though we're still going up, we got to slow down so we can hit 0. Now we're coming down, down, down. Now we're gaining speed even though we're going down. And then we slow so we can go back up again, right? So they can both be positive, or one can be positive while the other one's negative, or they could be both negative, because you could be falling in a negative direction and accelerating. Okay, so keep that in mind. So we're just going to take one function and we're going to find the first derivative and the second derivative. And then that will be, I think that's where I'm going to stop for this video. Yeah, that's absolutely where I'm going to stop for this video. So we're just going to go ahead and we're going to start with something somewhat simple. 5x squared plus 2x minus 3. Okay? All right, first derivative will equal the limit as x approaches 0 of 5 not f, x plus h squared plus 2x plus h minus 3 minus fx squared plus 2x minus 3 all divided by h. This time I'm going to, you've probably done it so many times by now, I'm going to do x plus h squared and multiply it by 5 all in one step. The limit as h approaches 0, that'll be 5x squared, 10xh, 5h squared, all divided by h, 5x squared, 3 minus 2x plus 2x, everything divided by h. So we have 10x plus 5h plus 2. So that means the first derivative equals 10x plus 2. Okay, switching colors now, right? The second derivative equals the limit as h approaches 0 of 10x plus h plus 2 minus 10x plus 2 all divided by h equals the limit as h approaches 0 of 10x plus 10h plus 2 minus 10x minus 2 all divided by h. The 10x cancels the 10h, not 2. The 2's cancel the 2's, and I'm left with 10h over h, which is just 10. So the second derivative is 10. Okay, now let's say I used x equals 3. Okay? Okay, my position would be 48 feet in the air. My velocity would be 32 feet per second. And my acceleration would be 10 feet per second squared. Apparently I have constant acceleration here. Okay. So, derivative, apply the limit process, watch your algebra. Apply the limit process, watch your algebra, and you've got this.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? And drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.